digital technology changes so rapidly. That is wrong. All of the digital Dac technologies that have been in existence today were there 30 years ago. And I don't want to produce products that's just a little bit better as an upgrade. And my design philosophy is to make it optimum from the word go, and not to change anything, but to get as close to perfection that we can get with that hardware.
สำหรับต้นปีนี้นะครับคุณล็อบวัตนะครับเชฟ Engineering and Design จากทาง Chord Electronics ให้เกียรติกับทาง Audio Force เดินทางมาร่วมเปิดตัวเป็นที่แรกของประเทศไทยนะครับและร่วมตอกย้ำกระแสอันยอดนิยมของ Dac Chord ในประเทศไทยนะครับซึ่งเดี๋ยวเราในคลิปนี้นะครับคุณธรรมนูญประทีปจินดาจะทำการสัมภาษณ์แล้วก็พูดคุยกับทางล็อบวัตนะครับและพูดถึงแนวโน้มของ Dac Chord นะครับเชื่อว่าหลายคนเนี่ยกำลังตื่นเต้นติดตามอยู่ว่าคอร์ด Dac เนี่ยจะมีอะไรใหม่ๆมาไหมนะครับคลิปนี้จะได้ชมกันนะครับเดี๋ยวเราไปชมกันเลยครับ
สวัสดีครับธรรมนูญที่จินดานะครับแล้วก็วันนี้ผมอยู่กับมิสเตอร์ล็อบวัตจากคอร์ดอิเล็กทรอนิกส์นะครับมิสเตอร์ล็อบวัตนี่เราตั้งฉายาเขาว่าเป็นพ่อมดดิจิตอลแห่งคอร์ดอิเล็กทรอนิกส์นะครับแล้วก็วันนี้มีสิ่งที่น่าสนใจแล้วก็การนำเสนอโปรดักต์ใหม่ที่คุณจะต้องตื่นตาตื่นใจนะครับเดี๋ยวฟังกันเลยนะครับ Hello
Hello It's lovely to be in Thailand again.
Good to see you. Okay. We call digital wizard. Okay.
I've been called a number of things. The problem I have here is that there's an awful lot of technical differences that separate my technology to everybody else's technology. For example, Dave is 8 years old. Why is it so old? Why hasn't it been replaced? Digital technology changes so rapidly. That is wrong. All of the digital Dac technologies that have been in existence today were there 30 years ago. It's not something that changes very, very rapidly. Because of the complexity that we've got with everything that I do, to make a fundamental change requires a considerable amount of work. And I don't want to produce products that's just a little bit better as an upgrade. We've always had the philosophy of making things a lot better. And that takes a lot of effort and time. And it requires sometimes new technological. And I don't want to produce products that's just a little bit better as an upgrade. Going back to your question, what separates my Dacs from other chip-based Dacs or other FPGA technology? There's a number of different things, and we can summarize it as 3 important factors.
Okay.
One is small signal accuracy, and small signal accuracy is really important so that you can perceive depth and detail resolution. And what I found, discovered, is that very, very tiny inaccuracies in signal amplitude degrades the ability for the brain to perceive depth. Because depth is something that the brain has to calculate. If you're hearing something that's 100 meters away or 10 meters away or a mile away, the brain is doing lots of different calculations to determine what that depth actually is. Very, very tiny errors screws up or disables the ability for the brain to perceive depth. I use incredibly small signals, minus 301 dB signals, as a test measurement. And if my digital circuitry, if my FPGA unit reproduces minus 301 perfectly, then you get very good depth and very good detail resolution. All other DAC technologies cannot reproduce minus 301. They cannot reproduce minus 160 dB. So this is a million times more capable.
160?
Well, they won't reproduce 160 dB, whereas we're looking at minus 300 dB. So it's millions of times more capable at resolving small signals. This means depth and detail resolution is better portrayed. And this is whether you're buying a Dave or whether you're buying a Mojo 2. They all have the same characteristic in that you can perceive depth much more accurately. Small signal accuracy is one very important thing. Another is something called noise floor modulation. All DACs create a certain amount of noise. And that noise, if it's static, if it's the same, it doesn't matter. But when the noise changes with the signal, then you get into big problems. And the brain cannot separate the sound of two different instruments playing together when there's noise floor modulation coming. Is to have a saxophone playing, for example, which sounds rich and warm and smooth sounding, and a trumpet which is bright and piercing. If there's noise floor modulation, then the saxophone will sound brighter than it should do, and the trumpet will sound less bright than it should do, because the noise is pumping up and down with the sound of the trumpet and the sound of the saxophone, and the brain cannot make a decision, is this the sound of the saxophone or is this the sound of the trumpet? It's the noise itself that's causing the modulation problem. That confuses the brain. So your ability to hear different timbres is being affected. Because of my unique DAC technology, I've got no measurable noise floor modulation. Doesn't mean there's zero noise floor modulation, it just means that we cannot measure it because it's so low. It's too small. And I can measure down to minus 180 dB and we can see no noise floor modulation. All other DAC technologies, for lots of different other reasons, have measurable noise floor modulation. What I've been working on is transients. And what is a transient? So a transient is when an instrument makes a noise or makes a sound from nothing. So that's the first transient. So when a note is starting, you get a transient. When a note suddenly stops, like if you stop the piano or if you hit the drum and stop the diaphragm from reverberating, it will stop. That's another transient. Transients are incredibly important perceptually. So when we hear things, it's not what's going on in your ears, it's the brain processing the data from the ears. And science doesn't understand how the brain does these kind of things. How we separate individual sounds out into individual entities, how we get the timbre information, how we get the bass and the pitch and all those kind of things. That is what the brain is doing. And what's completely key is transients. If you remove the transient information of a trumpet and remove the transient information of a piano, you can't tell whether you're listening to a trumpet or a piano. They sound very, very similar. So transients are very important for timbre perception. And of course, the starting and stopping of notes and where instruments are located in space, transients play a part on that. Even simple things of being able to separate individual sounds out, transients is important for this as well. So why I'm talking about transients and saying why perceptually it's very, very important. What's the problem with digital? The huge problem with digital is that it's sampled. So we have one sample, and then for CD 22 microseconds later, we have another sample. But your transient is somewhere in the middle. It might be right there, or it might be here, or it might be later. And we know from physiological science that the timing differences that the brain can perceive is zero. It can resolve ridiculously small levels of delay between the left ear and the right ear, for example. So the brain can resolve infinitely small timing errors, but the DAC has to take the sampled data and convert it into a continuous waveform and reconstruct the timing of the transients. If it doesn't do that, then your timbre suffers, your pitch suffers, your starting and stopping of notes suffers, the ability to separate instruments out into individual entities, that gets degraded. I'm the only person in the audio business that talks about transients and talks about transient reconstruction as being an enormous problem. And I don't know why other people don't talk about it.
Yeah.
Because it is obvious.
Yeah.
If you study psychoacoustics, you know that transients are important. If you study digital audio, you know that the problem of reconstructing of transients is an enormous problem. And that's something that I've been working on for the last 30 years in terms of improving the ability of the DAC to reconstruct transients. One is the amount of processing that's involved.
Okay.
So to reconstruct a transient correctly, you have to use a huge amount of processing.
Okay.
Chip DACs, they'll have a measure of your processing is the number of taps in the filter.
Okay.
A chip DAC will have 100 taps. As simple as that. So just 100 multiply, accumulate actions. But it's not the number of taps that's important as well. What's more important is the algorithm that's used to create the coefficients.
This is the key.
This is the key.
This
is the key. And what's unique about my WTA algorithm is that I've spent a lot of time listening to the coefficients and adjusting the coefficients with a formula. And my adjustment of the coefficients are down to 10 parts per million. So I change the level of a coefficient 10 parts per million. And you can hear it in terms of the sound quality changes. And optimizing that performance with thousands of listening tests has given me the WTA algorithm, which gives us a much more accurate way of reconstructing things.
WTA is what? Transient?
What's transient aligned?
Aligned.
So what I'm trying to do is align the transients.
Yeah,
Sure.
Right.
So we're going to be launching, at Munich.
Yeah, at Munich.
We're calling it the Quartet M scaler.
Why
Quartet? Because it has 4 million taps inside it.
Mostly is is a scalar is 1 million, right?
Scale is 1 million. So
This is 4 million.
this is 4 million.
4 million
Yeah.
is 4 times
Yep.
different, right?
Yeah.
And
It's got 5 200T FPGAs. So 5 of the devices that we use in the M scalar, there's actually 5 built into that. So there's other things that I'm doing inside. So there's 5 200T devices, which is the same device that we use in the M scalar.
okay,
So there's a lot of DSP cores. There's a lot of processing going on.
But you can tell the electronics is working and there's a lot going on purely because of the amount of thermal energy
Yeah.
that has to be dissipated.
that means the quartet is separately power supply, right?
Yes, there's a separate
Yes.
power supply.
And I think power supply is very, very critical for digital.
Yeah.
Yeah.
The issue we have here is trying to isolate
Yeah.
the noise from the processing
Yeah.
from upsetting the DAC.
Uh-huh.
We've got significant challenges with the scalar because it consumes a lot of power.
Okay.
The big issue is that the FPGAs create a lot of noise,
Okay.
and having 5 of them creating a lot of up to 10 gigahertz noise, that noise must be isolated from the DAC. People often ask me, why can't I have a scalar inside Dave? Problem is trying to isolate the noise of the processing from the analog section. And with 10 gigahertz, it's impossible to put it in the same box. So we need to isolate it, separate power supply, RF filters to filter out the 10 gigahertz. I've improved the BNC outputs so that the isolation is better, so that when it gets into the DAC, the noise doesn't affect the DAC itself.
Okay.
And there's a hell of a lot of work that's gone into solving that problem. So having a separate power supply is part of that issue. External clocks is a very bad idea. Because what you need is the clock to be very close to the analog circuitry. I worked as a silicon designer, as a consultant for major companies. I worked for 14 years doing half a dozen different audio devices. And you get given a specification. So you require, for example, a certain amount of jitter, and you have to have a certain level of noise coming out, and that's your specification. And the spec they gave me was 4 picoseconds of jitter, picoseconds of jitter, and 120 dB dynamic range. So I designed a DAC that met that. Then we had to make a change because they said that the noise, the problems you have with silicon chips are enormous. A lot of the problems are digital noise getting through the substrate and attacking the analog. And this one was a digital power amplifier, so it had quite a lot of digital noise. The design of the DAC itself, different DACs have different sensitivity to jitter. So one DAC will be very, very sensitive to master clock jitter. Another DAC will be insensitive to master clock jitter. Pulse array is the most insensitive to master clock jitter of all the different types of DACs that you can get. The other issue is that when you have a clock, you put it into an input buffer, it then goes to a level shifter, it then gets distributed throughout the die. Every time it goes through something, it adds 1 picosecond of extra jitter. So by the time you've got, let's say you had 1 picosecond coming through, by the time you're getting to the actual switching components, you're looking at a lot more jitter. What you want is to keep the connection from your clock to the active circuitry as simple as possible, because each stage of buffering creates more jitter and creates more problems. Having an external clock in another box is a crazy idea. It's technically stupid because you need an output buffer, that's going to add jitter. You need cabling, that's going to add jitter. You need an input stage, that's going to add jitter. You then need a phase lock loop because your frequency is wrong, and you use an analog phase lock loop, that's going to create more jitter, and that's going to create low frequency jitter. And low frequency jitter is very, very audible. And what happens with low frequency jitter is it makes things sound brighter and clearer because you've added some noise floor modulation. Because the low frequency jitter makes your nice sharp sine wave turn into something that looks like this.
Skirting.
It's skirting.
Yeah.
And that skirting makes things sound artificially brighter. So when you plug in an external clock, it sounds brighter. You think it's better. It's not. It's distortion. You're just preferring distortion.
But
what's interesting about it is that it sounds brighter and you think it's more impressive. But if you listen for a long period of time, you get more listening fatigue. And it's becoming more impressive, but musically wise, musicality is much worse. Because a less impressive sound is a warmer sound, a more natural sound.
Okay.
So we don't do external clocks.
Okay.
No.
No need.
No need. The problem with firmware updates is it means you've got a fault. Software doesn't work. They don't care. They just chuck it out, and then they'll give you an update and get it to fixed. My background is designing silicon. You can't go through a process of doing it because every time you have a new mask set, that's another $750,000. So you have to get the design right from the word go, and simulate it and check it and measure it and use FPGAs and test it. And my design philosophy is to make it optimum from the word go, and not to change anything, but to get as close to perfection that we can get with that hardware. So when we do a new design, when I do a new design, there will be hardware changes.
Okay.
Because the FPGA is optimum for that particular function. So for example, Mojo 1 to Mojo 2 was a big change in performance. But to do that, I had to do lots of hardware changes because of power dissipation and battery and all that kind of stuff. The project that I have been spending 4 or 5 years working on is the Ultima Dac. And we hope to launch the Ultima Dac either this time next year or maybe later this year. That's the project that I'm working on at the moment for Dacs, not Dave too.
And the most important thing is that Dave, with the work that Rob has put in on the
quartet
scaler, it means that it raises the overall performance of Dave.
Enjoy music.
Enjoy music. Just enjoy music. Don't worry about
external clocks.
External clock.
Just enjoy the music. I mean, at the end of the day,
forget that thing.
That's all that's important. The ability to enjoy music, for your spine to tingle. That's all that I want to do. And when you listen to live, unamplified music, it's very easy to get emotionally involved with the music. And that's all I'm trying to do, connect with the original emotional performance. So enjoy music.
ได้ยินชัดๆแล้วนะครับว่า external clock จำเป็นสำหรับคอร์ดไหมคอร์ดบอกไม่ใช่เลยไม่ใช่ทางแล้วก็เดฟคุณมีเดฟอยู่แล้วคุณจะต้องเก็บเงินได้ละเตรียมตัวสำหรับคอร์เทจก็คือสเกลเลอร์สำหรับมันแล้วก็ power supply ซึ่งจะเรียกว่าเป็น Cortex เดฟคุณยังใช้ได้อีกยาวนานนะครับเดือนพฤษภาที่จะถึงที่มิวนิกเนี่ยคงจะมีรายละเอียดเยอะๆนะครับแล้วก็ต้องติดตามกันนะครับขอบคุณสำหรับวันนี้ครับ
หลังจากที่เราได้ฟังคุณธรรมนูญสัมภาษณ์คุณล็อบวัตแล้วนะครับเดี๋ยวผมจะลองมาสรุปคร่าวๆให้ฟังกันนะครับก็สำหรับปีนี้นะครับหลายท่านที่กำลังดูแนวโน้มของ Dac Chord อยู่ก็บอกเลยว่าสบายใจได้เพราะว่ายังไม่มีผลิตภัณฑ์ที่เป็น Dac Chord เนี่ยออกรุ่นใหม่อย่างแน่นอนนะครับทางล็อบวัตเนี่ยยังยืนยันว่า Dac Chord ในปัจจุบันนี้ยังเป็นที่สุดของคุณภาพเสียงที่สุดของคุณภาพเทคโนโลยีและการค้นพบเทคโนโลยี WTA ที่เป็นเอกสิทธิ์นี้ยังเป็นจุดสูงสุดของเทคโนโลยีแดกของคอร์ดที่ทำให้ชื่อเสียงโด่งดังไปถึงทุกวันนี้นะครับสำหรับลูกค้าที่กำลังเล็งนะครับหรือว่ากำลังศึกษาของคอร์ด Mojo 2นะฮะคอร์ด Q-Test คอร์ด Hugo TT2 คอร์ด Hugo 2นะครับหรือว่าจะเป็นคอร์ดเดฟรุ่นแฟลกชิพเนี่ยก็สามารถตัดสินใจเล่นได้เลยนะครับทางล็อบวัตยืนยันว่ายังเป็นที่สุดและยังสามารถเล่นไปได้อีกยาวนานนะครับและจะมีผลิตภัณฑ์ใหม่ที่จะมาเสริมตัว Dac Chord นี้ให้ต่อยอดขึ้นไปได้อีกโดยที่ Dac Chord ทุกรุ่นจะไม่ตกรุ่นครับ
Digital to analog conversion takes digital data and converts it into an analog signal that we can hear. This digital data can be represented by ones and zeros in a digital file, flashes of light through an optical cable, or a voltage being turned on and off in a conductive wire. Let's look at the difference between a standard chip DAC and a DAC that uses Chord technology. Standard chip DACs are inexpensive. They have predictable, predetermined characteristics and they're mass-produced. They're in everything that makes a sound, and the same chip could be in an expensive DAC or a simple portable player. Chord, however, takes a very different approach, a much more powerful one. We designed the chip from the ground up with unique coding. With our DAC, we control everything and reproduce the original waveform with astonishing accuracy through the use of Rob Watt's multi-award-winning technologies. Looking at the board itself, you may not initially see a difference. A standard chip DAC uses the standard chip that we talked about earlier. Chord DACs use a very sophisticated, custom-coded, field-programmable gate array, or FPGA. Essentially, this is the powerhouse of the device, where the complex filtering and noise shaping of the digital data takes place. We use FPGAs because they allow us to create a completely custom digital circuit that is several orders of magnitude more complex than a standard chip DAC. The filtered noise-shaped data from the FPGA is received by the flip-flops, which convert it into an analog signal. Chord uses excellent crystal oscillators. These are the beating heart of the DAC, pulsing a voltage at fixed ultra-fine intervals to send data. Jitter sound quality problems are eliminated partly because of the flip-flops having a direct or pure feed from the crystal oscillator. Regular chip DACs typically have an internal feed which succumbs to switching noise running through the silicon of the chip. These regular chip DACs typically operate at a frequency of only 6 MHz, giving poor resolution. Chord oscillators operate around 20 times faster at a frequency of 104 MHz. We do this in order to faithfully reproduce incredibly small micro details from the original recording. This increased speed also reduces noise, which in turn yields amazing resolving power, so you'll hear things on your recording that you've not experienced before. The WTA interpolation filter is one of the main reasons for requiring such powerful FPGAs. The WTA filter's primary objective is to reduce the margin of error in terms of timing. This is crucial for reconstructing transients, where these sonic cues are responsible for accuracy, quality and clarity of timbre, articulation, soundstage, pitch and rhythm. This WTA filter has 500 times more processing power than a conventional, industrial or military DAC chip, and is yet another reason to run the crystal oscillator at 104 MHz. The DAC also uses a unique technology, pulse array. Here is an illustrated example of a 10-element pulse array DAC. Many standard DACs use a single element line that switches slowly between states, but this approach has poor resolution. What you can see here is that each individual element has a rising edge of data cancelled by a falling edge. This results in a much higher resolution signal that is immune to jitter. Due to this signal-independent activity, all switching errors are eliminated, which provides benefits when dealing with distortion and noise floor modulation. Noise floor modulation is when the residual noise of a DAC varies with signal. It's very annoying, and regular DACs have very large amounts of it. With chord DACs, noise floor modulation is not measurable. This gives a very smooth and refined sound quality. Instead of using a semiconductor chip, op-amps or other active electronics, Chord uses a discrete output stage to amplify the converted analog signal directly from the flip-flops. The signal only passes through 5 individual components and helps keep the signal path very simple. Because of this, along with the fact that the volume control is handled digitally inside the FPGA without loss of information, due to Chord's unique oversampling process, there is very low small signal distortion in comparison to using active electronics or signal paths with hundreds of components. Simple, short and tight tolerances of components give us low distortion and noise. A Chord DAC has full control, and it can drive headphones and IEMs down to very high and low impedances. Thus, it perfectly drives all headphones and IEMs. The signal that comes from the DAC itself is unadulterated and completely pure, allowing you to enjoy your music like never before.